Okay, so now we're going to analyze graphs of functions. And some of this should be somewhat familiar. You know, vertical line test is a way to determine whether something's a function. Finding the zeros of functions, which probably sounds familiar, but maybe you need to be reminded what that means. And then there'll be some things you may not have seen before: increasing and decreasing, relative maximum, relative minimum of functions. Okay, so the first thing that we do here is we determine the domain and the range from the graph, right? Now we're not dealing with an equation that we could look at and say, is there any dividing by zero going on? Is there any square roots of negative numbers going on? You know, we don't have that to look at. All we've got is a graph. Right? Now, when you look at these graphs, you got to think because we don't even have the equation to look at. Sometimes you do actually, but you don't this time. When you see this line go down like that, you assume it keeps going. It doesn't just stop at that point. You know, it would be nice if they just put little arrows on the end of this, but you know, we assume that this graph goes on forever. And because there's a little bit of a tilt to it, right? Like on this side here, that means it's going forever to the right and forever down, right? There's a little bit of a component which is that way. There's a little bit of a component which is that way. And same thing on this side, right? It's going forever to the left and forever down. So, and just for grins, put that in there. If a graph goes forever to the left and forever to the right, what would be its domain? All real numbers, right? So we would say because of this, right, domain is all reals. And again, the book, they use this interval notation. I just can't remember right now whether we've done this yet, but if not, this is where it all comes up, right? When you use parentheses, it means that this interval does not include the endpoint. And when you use infinity as an endpoint, you know, by definition, you never get to infinity. So you use round parentheses to mean it goes from x equals negative infinity to x equals positive infinity. Any x value in between is included. Does the range look like it goes forever? The range are the y values, right? Does it look like it goes forever up and forever down? No, it doesn't, right? Where is it limited? It looks like it's going up only this high, and then it goes back down again, right? It does go forever down. I mean, those arrows are going down. So how could we describe the interval where you have y values? Yeah, I mean, you could say it'd be perfectly fine for me if you said the range is y is less than or equal to 3. Okay, that's fine. That means everything less than or equal to 3, and it's equal because you clearly have the point 3 that's on there, right? Now, in terms of the intervals, the way you would write that, you always have the lesser number to the left, and since that's going to be negative infinity, it'll be a round parenthesis to mean you don't ever get to negative infinity. And then the bigger numbers on the right, that'll be the 3. And that one, since it includes 3, use a square bracket, right? The square bracket means includes that endpoint. Includes 3. Now, I also had in this example another thing which sometimes we struggle with, and that is the function values. How is it that you tell, you know, the f of 0 from a graph? We know if we have the equation, we just plug in, right? But how do you find f of 0 looking at a graph? Well, you go to x equals 0, right? There's x equals 0, and then you go up to the graph and you read off the value, 3, right? So you would say f of 0 equals 3. How about f of 3? I mean, go to x equals 3, and then follow it down to the graph. What's the y value? -6. So f of 3 equals -6. Okay. Let me go back to the text right here and contents. Analyzing the graphs. I think there's a lot of graphs in here that just looking at all the graphs they have, you should be able to kind of tell domain and range just looking at them. Like when you see a line that's going on, it's tilted like that, that means it's going forever down, forever to the left, forever up and to the right. Domain, all real numbers. Range, all real numbers, right? There's a parabola, right? We assume it goes on forever to the left and to the right. So domain is all real numbers. And we can, now, because we've got the equation, you can say there's no dividing, there's no square roots, all real numbers. But the range is limited, right? It only goes down as far as -4, y greater than or equal to -4. Even a funny graph like this, right? The x values that are included do not include the numbers in between -1 and 1. So you would have two pieces of the domain. X is less than or equal to -1, and x is greater than or equal to 1. Right? Just don't include those values there. And what does it look like the range is? The range, where do the y values start? They start right here, right? They start in the x-axis, which is y equals 0, and they go up from there, y greater than or equal to 0. So you ought to be able to look at graphs and kind of tell what domain is and range, just estimating from the graph. How about a circle like that? What is the domain? It looks like the radius is 5. How could you describe the domain? Well, look, every point in that circle is in the domain, right? So you've got some values of x that are in between -5 and 5. So how can we describe all those infinity of points that are in between -5 and 5? Best way, 3-part inequality. -5 is less than or equal to x is less than or equal to 5. Or if you use the brackets, you would use square bracket, -5, comma, 5, square bracket. That means everything in between -5 and 5. So anyways, let's go back to this. Now, in order to we know what the definition of a function is, right? A function means there's only one y value for every x value. But when you've got an infinity of points, then you can't like look at them all and determine that whether you have repeated x values. You just won't be able to do that. So instead, we have what we call vertical line test. In the vertical line test, if you can imagine anywhere in the graph that you could pass a vertical line and it would cross at more than one point, then it fails the test. Like this one fails the vertical line test. And just imagine this is x equals 2, right there. So if I've tried to find the function value at x equals 2, I would go to x equals 2, and then I would go to the value of the graph. That means I would go up, and I'd come up with a value, and I'd go down, I'd come up with a different value. But two values for the same x, not a function. That's why vertical line test is a check for function or not. This one, can you imagine anywhere in there they could have drawn that vertical line and had it fail? No, that's a function. How about this one? It's a funny graph, right? It doesn't have its domain is not all real numbers because it's missing the values in between -1/2 and +2. Is that right? No, it's actually between 0 and 2. But yeah, that passes a vertical line test. So you would say this one fails vertical line test, not function. Right? This one passes, so it's a function, and this one passes, so it's a function. Okay, use the vertical line test to decide whether this is a function. Is it a function? Sure. I mean, I can't see anywhere on the graph, where it would cross in more than one spot. So you would say, passes it. I can draw a line just because it's fun, right? Make sure it's a thin line. There's our line. So we're going to say that passes a vertical line test. So passes vertical line test. Therefore, function. Later on, we'll get a horizontal line test. We get both. Okay, finding the zeros of a function. Right, here's a function. We know it's a function because it starts out with f of x, right? That's a function. When they say the zeros of, it means the values of x for which f of x equals 0. So it means replace the f of x with a 0. Now, graphically, since this is all about analyzing the graphs of functions, where does x equal f of x or y equal 0? On the x-axis. So where do you look for the zeros of a function? You look for them wherever the graph crosses the x-axis. Those are called the zeros of a function. At least for now. Okay, so now you can find these things any way you can. If it's factorable, you could factor it. If not, you could use quadratic formula. If not, you can graph it. Is this one factorable? How do you tell if it's factorable? You'd say 2 times negative 24 is negative 48. Can you think of factors of negative 48 that add up to 13? If you can, it's factorable. If you can't, it's not factorable. And the answer is you can. Positive 16, negative 3. So we would go 0 equals, and we'd split up the middle term using those numbers. All right, then we would group the first two terms, group the last two terms, factor each set of parentheses, right? What's the greatest common factor between 2x squared and minus 3x? X, just one x. So we would say x times 2x minus 3, right? What's the greatest common factor between 16x and negative 24? Eight, right? It's 8 times 2 is 16, 8 times 3 is 24. So take out an 8, 2x minus 3. And then because you have the same thing in parentheses, 2x minus 3, then the last step is, right, you're going to factor the 2x minus 3 from both terms. What's left if I take 2x minus 3 away from the first term? X. What's left if I take 2x minus 3 away from this term? Plus 8. Right. Now, you're not done. That's just a factoring of it. What are the values of x that make this true? Negative 8 and 3 halves, right? You got to cancel the 2, right? Don't just look at it and say 3, right? Because that's actually not an x. It's a 2x. So if you need to, just make a little equation, right? 2x minus 3 equals 0. 2x equals 3. X equals 3 halves. So and this one was x equals negative 8. There's the negative 8. There's the 3 halves. Let's see. Do you remember how to find it in the calculator if you have to find it? Do you want to go through that? I mean, it should be something you know how to do. It should just be, those steps, are simple. Because a lot of times we're looking for these things, and it's not an exercise in these calculator steps. The calculator steps are kind of assumed. But if we struggle with just remembering those, then we have trouble. So let's put this in the calculator and see how we find the zeros. Okay, so go to the y equals. Y equals means it's a function. Solve for y. Put in the 2x squared plus 13x minus 24. Right, you can look at the graph. Don't really have to, but you could look at it. That's where I got the graph that I showed on the screen. Okay, now to find the zeros, right? Don't just hit trace. If you hit trace, this is what a lot of students do. You just hit trace and then you start like letting the thing scroll until you see it come close. Let me go on the other side, which is closer. There it goes, right? And maybe you would write down 1.48. That's not the zero because y does not equal 0. Right? You could try to go one more, but it jumped over the line. Right? So the closest you got was that one that was right below. That is not the 0, right? Because y does not equal 0. To find the 0, you would go second, trace, and then it says right there, 0. And if I hit 2, and now when it asks for left bound, it's asking us to put an interval, a left side to this and a right side to this, to say we want to look in between those two numbers. So when they're saying left bound, they're just saying put in a number which is to the left of that 0. Not to the left of that 0, but left of this 0. And you could either do that by moving your cursor so that it's clearly to the left, or just enter a value that looks like it's less, 0. And then it'll ask you for the value on the right of that 0. Again, it could be anything that's on the screen right there. Or you could move the cursor until you see it go above and to the right, enter. And then when it says guess, it's asking, do you want to guess in between those two numbers you just entered on the screen? And if you're okay with those, you hit enter. And it didn't. 1.5, 3/2. Like that's how you do it. Okay, finding the zeros of a function. In this case, I mean, you could see the function. This is a square root function. It's been moved 2 to the right because of the -2. Right? The zeros mean 0 equals the square root of t minus 2. You could probably tell just looking at it what value of t is going to make that equal 0. 2. 2 minus 2 is 0. Square root of 0 is 0. If you were going to solve it, you would square both sides, and you get 0 equals t minus 2. T equals 2. So the 0 is 2. If you looked at it on the graph, you should be able to kind of eyeball that and tell. It looks like it's at 0. All right, find the zeros again. In this case, and this is a kind of particular case that it should be easy, and we make it into something harder than it needs to be. But when we say find the zeros of this function, which is a rational function because it's a fraction, right? That means find the values of x that make x squared minus 2 over x minus 1 equals 0. But in a fraction, if a fraction equals 0, which part of the fraction must be 0? Not the denominator. That would make it undefined, right? The numerator, right? If you have 0 over a number, then that equals 0. So if we want to find which values of x are going to make this whole thing equal 0, in fact, you don't need to even look at that. It's not coming from the denominator. It's only coming from the numerator. So set the numerator equal to 0 and solve. Oops, x, darn it. Okay, edit. Oh no, don't fail on us. Let's see if I can come over here and change some thinking. So you could see, what are we going to do next? Take this, move the 2, x squared equals 2, take the square root of both sides. The value is plus or minus the square root of 2, right? The plus, that's the minus. It's about 1.4, negative 1.4, positive 1.4. Let me see if I'm going to have to kill this thing. Come on, come on, come on, come on. Did I just lose it? No. Okay. Now it's starting to think again. Okay, let's see if it says not responding. Not responding. Thank you very much. Okay, and that is off. Kill it. Go back. Okay, let's see. Yes, and close. Now, was that ours? That was ours. So we are. We should have all of our work still in there. Okay, we were there. So x equals plus or minus the square root of 2. Okay, now we're going to talk about intervals of increasing and decreasing. And I think you probably can see on a graph what it is that represents increasing or decreasing. The problem comes in how do you describe it, right? And we make mistakes on that all the time. The thing to remember about when we say find intervals of increasing and decreasing, what we mean are intervals of x, not y. Don't include the y values ever. We only want intervals of x. And what we mean by the increasing and decreasing is what are the y values doing as the graph is going and the x values from left to right, right? So from here to here, what is the graph doing, or what are the y values doing? They're going down, decreasing, right? From here to here, as you go from left to right, it's increasing. It's kind of like negative slope, positive slope, decreasing, increasing. And if it's not doing either one, it's constant, right? But we wouldn't, let's say I was going to name it on this graph right here. The interval of decreasing, and this one they've given, this has got a hard endpoint right there at -2. I would say this is decreasing from -2 to 0, right? I'm not putting the y value of 4, right? That's not part of this. It's intervals of x only. So, and because it's got a closed circle, I'm using the square brackets to say it includes that. It probably should not. It should probably say round here, just because we can't include it in the interval that's decreasing and include it in this interval here. It's doing one or the other, right? It's not doing both. right? This interval, in fact, let's just make that correct. Let's change that to a round. Because when we say this next interval, right, the constant interval, this one right here, that starts at 0 and it ends at 2. And then what about the increasing? The increasing is starting at x equals 2, and then it goes until 4. So we'll say 2, 2, 4, up. Make that a square bracket, just because it's closed endpoint. So that's the main mistake you're going to make, is you're not going to use the intervals of x. You're going to start saying things like 4 to 1, 1 to 4, right? Those aren't part of the way you name the intervals. They're just intervals of x values. Like this graph, what does it look like it's doing? Is it ever decreasing? No. Does it look like it's constant somewhere? It kind of looks like it might be, but it's not. It's increasing. It's f of x equals x to the third, and you could show it. It may look like it's flattening out, but actually there's a little bit of a slope there. It's constantly increasing. So we would say the intervals are increasing only, and it goes from negative infinity to positive infinity, over all real numbers. Okay, what about this graph here? What is it doing from here to here? Increasing? What's it doing from here to here? What's it doing from here to here? Yeah, and notice, unlike the one that we had on the last slide, they don't have fixed endpoints here. So what do we assume these lines are doing? They're going on forever, right? This arrow goes on forever. This goes on forever. So if I'm going to name the intervals, right, this interval to the left of that dashed line, it's decreasing, right? What's the left side of that interval? Since it goes on forever to the left. Negative infinity, right? And then where does it stop increasing? -1. X equals -1. Right? Don't say -1 to negative infinity, because now you've switched the order. These things always have the lesser number to the left. So that's an increasing. Okay, now it's decreasing up until that, right? How would we call that interval? Those are y values. You just use the y values, and we're only using the x values. -1 to 1. Okay, and then what about this interval from here to here? The left side of it would be 1, and the right side, since that goes on forever, infinity. That's an increasing. Again, this is a piecewise defined function, right? What's it doing up from here to here? Increasing, right? So we would say it's increasing negative infinity to 0, x equals 0, right? So don't look at the y, just look at the x, right? And then it's constant from here to here, so that'll be 0 to 2, and then it's decreasing from 2 to infinity. Increasing, decreasing. Like I said, I think you probably see it, right? It's just a matter of naming it correctly. Don't use the y values. Okay. Now, the relative maximum and minimum points mean any place on the graph where the graph changes direction. Like here it was going down, and then it turned around, now it's going up. Right? That makes this point a relative minimum point. It's not necessarily the minimum for the whole graph. It's just the lowest point in that area, right? If I go a little bit to the left, it's more. If I go a little bit to the right, it's more. this is also a relative minimum, right? Because it's the lowest point in its area right here. And that's the thing is, because they're just relative minimum, you could have more than one. There's two of them on this graph, right? You're not looking for one minimum or maximum. You know, if I thought this graph went on forever, and this graph went on forever, then, you know, clearly it's got lesser values there, but it's not a minimum. We're really looking for, where does the graph change direction, right? And you could see the maximum points, right? That's where it changes direction, but now it's changing from going up to going down, from going up to going down. You would say it's increasing in between those points, right? And it's decreasing in between those 2 points. And what's it doing right at the point? It's flat. It would have a zero slope. It has a positive slope, negative slope, zero slope. Now, I'm not sure what I got on the next slide. Let me see. Okay. For the most part, we can't really calculate maximum and minimum points yet, except for using the calculator. It becomes like the main focus of the first part of calculus is, how do you find those points on the graph? And it's actually pretty simple to find. But we don't have the, let's say, algebraic kind of ways to do that now, except for, you know, if you're talking about a parabola, then that minimum point is not just the relative minimum, it's the absolute minimum, it's the vertex, and we have ways to find the vertex of a parabola, negative b over 2a, if you remember. But for the most part, we don't have ways to find them other than from the graph, just looking at the graph. So in this one right here, do you see the relative minimum? Can you estimate what the coordinates of that point are right there? Let's see, this is -1, -2, that's a -3, oops, -3, this is 1. So what would be the coordinates of that point? X equals, looks like it's in between, how about we'll call it a half. If you have to read it from a graph, you just have to estimate, right? So we're going to say it has a minimum at 1/2. And what does it look like the y value is? It's in between -3 and -4. To me, it looks like it's closer to -3. How about I'll say -3.3, something like that. So you would say that the minimum value of the function is -3.3. It occurs at x equals 1/2. If you were asked for the minimum point, it's the whole thing, right? 1/2 comma -3.3. And notice now, we're back to using the parentheses to mean a point, right? Not to mean an interval. So it does get kind of confusing like that, but the book uses those round parentheses and square brackets to be their intervals. So you don't want to confuse the two. You know, I think we have to do parabolas, quadratics and parabolas. I don't think it's in this chapter, but when we get to them, we'll actually find that point. But for the rest of them, and we're not going to do it because I don't want to spend to do things I can only do in the calculator, right? But the same place you found the zeros, second trace, there's minimum and maximum. You can find them with the calculator, right? But if you get asked a question, you'll be given the graph and said, just estimate it, visually estimate. What does it look like it is? And let's see, one more slide. Nope, that's it. So we did the vertical line test, right, for functions. We know what we mean when we say find the zeros of a function, and finding the intervals on which functions are increasing and decreasing. And determine relative maximum and minimum values. I think when we get to those, let's see, we're saying 7 to 23, 31 to 37. Let me pull that up. Right. The first set of problems are finding zeros, right? The next set of problems are increasing, decreasing, And it might have, let's see, it says 31 to 37. And that's it. Okay. You're good because you got graphs for it already. I was trying to remember from pre-cal, I think they had to do some where they actually had to graph it to find the maximum and minimum, just visually. Okay. So that is that.